Stress corrosion cracking, or SCC, is a material failure induced by a combination of three things: a specific corrosive environment, the influence of tensile stress, and environmental temperature. All metals have the potential to fail as a result of stress corrosion cracking. Here's Dan Janikowski with some expert insight into SCC.
Stress corrosion cracking, or SCC, is a very different failure mechanism than other types of corrosion, and the solutions to prevent it can be equally different. SCC is a material failure mechanism generated from a combination of tensile stress, a specific corrosive environment, and elevated temperatures. For stainless steels, SCC can occur in higher chloride environments, such as power plants, and in alkali solutions used by the process industry. Total stress is a combination of stresses from many sources, including thermal stress, internal pressure, and other environmental sources. However, the largest potential source for stresses can be the residual stresses from the tube manufacturing process. SCC is considered to be a catastrophic failure mechanism, primarily because of the difficulty in detection and the unpredictable damage it can cause. There are two solutions to minimize the risk of SCC. One is to choose an alloy that is resistant to SCC as it applies to your application, or by simply specifying tubing which has low residual stress. Knowing what causes the SCC and what alloys are susceptible to them is an important part of the material selection process.
SCC is characterized by cracks propagating either transgranular or intergranular along grain boundaries. Different metals are sensitive to cracking from different media. For example, stainless steels are sensitive to chloride environments, copper alloys are sensitive to ammonia environments, and higher strength steels are sensitive to hydrogen sulfide. SCC can be attributed to the combined action of three factors: tensile stresses in the material, a corrosive medium such as chloride-bearing or hydrogen sulfide media, and finally the selected material susceptibility to SCC. SCC is a very different mechanism than pitting or crevice corrosion. The drivers can be quite different, and assuming that one or the other is the source of a failure without investigation could lead to repeat failures. SCC can also be difficult to predict. A process unit may have years of trouble-free operation and appear fine to the naked eye, when sudden failure can occur. While most of the surface remains unattacked, fine cracks which penetrate into the material are enough to cause a catastrophic failure under certain conditions. SCC failures can be caused by both design issues and/or operation. When they can be seen with the naked eye, stress corrosion cracks and fractures are brittle in appearance. Under microscopic view, stress corrosion cracks can have intergranular or transgranular structures, which are distinctly different than what appears across the remaining surface that's not impacted. Stress corrosion cracking can be caused by applied stress, which is a load applied directly to the metal during service, or residual stress, which can be the result of a prior forming process, welding, machining, or grinding. The impacts of both types of stress on metals are often underestimated or unacknowledged. Stress concentrators can also aggravate the situation. Some of these sources include corrosion pits and intergranular corrosion, which can come from various sources, machine marks, dents, and gouges from material handling or in manufacturing, and incomplete or rough welds, to name a few. It's important to know that all fabricated metals inherently have a certain amount of residual stress levels. This can range from 25 to 50% of their yield strength. So regardless of applications or process, it is something that is always present in any metal. There are no mandatory requirements for measuring for SCC in manufacturing or operation. So the prevention strategy for SCC is in material selection or additional secondary processes of the material to reduce residual stress levels. Annealing is one way to reduce stress and an effective method of mitigating stress corrosion cracking. along with other secondary processes your supplier may recommend. The best method to reduce the potential for SCC, however, is to specify the correct alloy which offers the highest degree of cracking resistance for the application. You can find additional information on alloy properties on the Flat Roll Mill's website. However, your supplier should also have the expertise in-house to offer guidance in alloy selection for your application. Additionally, for tubing and pipe products, you can specify residual stress testing as part of your purchasing requirements. The alloy consideration and analysis should go beyond the design criteria alone and factor in assumptions for changes in operation, as well as unforeseen environmental factors, inputs, and evolutionary changes. Make sure you understand the operational environment and variables such as load variables or exposure to temperature changes so you can reference them in your selection or convey that information to the expert assisting you in alloy selection. Be sure to consider the potential effects of stress corrosion cracking in the design and material selection phase of your project, or discuss with your supplier for additional insight and guidance.